Hi everyone, this is Mrs. GA, and today we're going to be solving exponential and logarithmic equations. All right, I have a quick warm-up for you guys, so pause the video and give it a try, and when you're ready to check, you can hit play. All right, go ahead and check your work. So here we can use the quotient property to rewrite these three logarithms as a single logarithm, which becomes log base 3 of 27, which is 3. And then here, same property. Remember, any negative exponent, the value goes in the denominator. And if you simplify this, you get common log of 100. Remember, common logs have base 10, so it simplifies to 2. All right, so first, today we're going to be solving exponential equations, which will involve us using logarithms, which is the inverse of an exponential equation. So first, we're going to try our best to isolate the term with the exponent. And then we have a few different options here, and I'll show you all the different paths you could take. So one option, which a lot of people really like to do, is to take the log of both sides, and it's usually helpful to try to match the base of your logarithm to the base of your exponential term, but you don't have to do that. You can actually take any base logarithm of both sides and it will eventually work. Another option after it's isolated is to rewrite the equation in logarithmic form and then simplify from there. And sometimes you have to do a few extra steps to finish solving, and you may also need to use your calculator for a decimal approximation. I will be asking for both an exact and a decimal approximation, so we will be using also that change of base formula to help us plug into our calculator. All right, so let's look at this first one together. Again, we're going to provide an exact answer and one rounded to the nearest thousandths. So first, we're going to want to isolate our term with the exponent, which is the e to the 4x. So we can divide both sides by 5. Okay, so from here, I'll show you two different paths. So I'll write the same thing over here. Okay, so path 1 is to take the log of both sides. Now, since this term is base e, I think the easiest thing to do is to take a base e log of both sides, which of course is a natural log. So we'll take the natural log of both sides. And the reason why we would do that is, remember, there's a property where if these two bases are the same, so base e, it simplifies to whatever your exponent is. So on the right side, this just simplifies to 4x, and then we can divide by 4, so natural log of 2 all over 4. Notice it's not the natural log of 2 over 4, it's the natural log of 2, and then we divide that by 4. Okay, so this is the exact answer. And if we want the decimal approximation, we would just plug that into our calculator, which is actually nice because your calculator should be able to calculate common logs. So the decimal approximation for this should be 0.173 if you round properly. Now, another way of doing this, again, is instead of taking the natural log of both sides, we could rewrite this just as a logarithmic equation. So I see the base is e, so I know it's natural log of 2 equals 4x, right? Because logarithms define the exponent, so this must mean natural log, so e to the 4x equals 2. So from here, look, we're right at this step. So it kind of saves us a step in this case, and then we would just divide by 4 and you get the same thing. So whether you're taking the log of both sides or you're simply rewriting it as a logarithmic equation, either way, we will need to use a logarithm to solve these types of equations. All right, let's try another one together. So here, again, let's isolate as much as we can. So I'm going to add 4 to both sides. And now I'll do the two different paths again. So here, since this is base 5, I think the best thing we can do is take the log base 5 of both sides. And remember here, if the bases match, it simplifies to the exponent. And there you have it. So this is the exact answer. Now to plug it into our calculator, your calculator can't do base 5 logarithms. We'll have to use that change of base formula, and we could rewrite it with either a common log or a natural log, and then we'll plug this into our calculator. and we should get approximately 1.490 if you round properly. Now again, another way of doing these is to rewrite as just directly into a logarithmic equation. So I see the base is 5 of 11 equals x. So you can see if you do that, it actually gets you straight to the solution, which is what we got here. All right, so go ahead and pause the video and give this one a try on your own. You could use whatever method works best for you. All right, go ahead and check your work here so you can see the two different methods that I used. Here again, I think the best route to go is to take the natural log of both sides, so the left side simplifies nicely. And you'll see here, after you've done that, you still need to do one step to finish solving. So our exact answer is natural log of 75 over 2 plus 1. So notice the plus 1 is separate, and here's our decimal approximation. All right, I have another one for you to try. So again, please pause the video and give it a go. All right, go ahead and check your work here. So I took the log base 6 of both sides, or you could rewrite it directly into logarithmic equation. Then you do need to divide both sides by 3 to finish solving. So here's an exact answer, and then I use the change of base formula to rewrite it like this so I could plug it into my calculator. Just be careful when you're plugging this into your calculator. You could do log of 12, but when you hit divide, you need to group your denominator, or else it will only divide by 3, and then it will actually multiply by log of 6. So you have to tell your calculator that the entire product is your denominator. So you should get this decimal approximation. So now that we know how to solve an exponential equation, we can go back and work through some problems from concepts we learned earlier this unit. So this is a compound interest problem. So it says, suppose $250 is deposited into an account that pays 4.5% interest compounded quarterly. So we can model that. So remember, it's your principal, which in this case is 250, times 1 plus your interest rate as a decimal divided by the number of times you compound per year, times that same number times t, which is the number of years that's gone by. So this models this account, and they ask how long would it take for the account to contain at least $500. So here they're saying the value is 500, and we're actually solving for t, which you can see is in the exponent. So this is an exponential equation. So we'll start by dividing both sides by 2, or by 250, sorry. All right, so now in this case, we don't really want to take the log of this base. So something we can do, we could just take the common log of both sides. So common log of 2 equals the common log of 1 plus 0.045 over 4 to the 4t. And then from here, we can use that power property. We can move this out front to the numerator. And notice I'm just keeping this right here like this. We'll plug it all into our calculator at the end. So I'm going to say try not to round until the very end. And then here to solve for t, we can divide by 4 and this entire logarithm. So we get t equals the log of 2 divided by 4 times the log of 1 plus 0.045 over 4. And I know this looks ugly, but really we're just going to be plugging this into our calculator. Just remember, when you do that, we do need to group our denominator. So take a moment and plug it in. So when I plugged in, I got, and I'll just round to the nearest tenth for this one, it doesn't specify, got about 15.5. So it's about 15.5 years to contain that amount. Now the nice thing about a problem like this is we could actually take this t-value and plug it into our original model to check that it actually yields a value of about $500, which it does. But again, I would say if you have the time, plug it in to check your answer. Okay, so now that we've covered exponential equations and how to solve them, now we're going to be solving logarithmic equations, which you could probably guess will involve us needing to use exponents. So first we're going to isolate, just like we did with the exponential equations. And sometimes, if necessary, we will need to use our properties of logarithms to condense multiple logarithms into one, so we can then isolate them. So we will be using the product and the quotient property a lot for these types of problems. And then once you have it isolated, you can simply rewrite the equation in exponential form. And then maybe you'll have another step or two to finish solving. But for these, the important thing to know is that you have to check your answer because logarithms have a restricted domain. So I want to remind you, if you have like something like this, that our a value, right, well, it will never be 0 because it's impossible to take any base, raise it to a power, and get 0. And our a value, whatever is here, must always be greater than 0, right? Because you can't take a positive base, which by definition, all logarithms have a positive base that isn't 1. You can't take a positive base, raise it to a power, and get a negative number. So you need to make sure that whatever x value you get, if you plug it into your equation, that this value is not 0 or negative. All right, let's give this first one a try together. So here we're going to start by isolating our logarithm as much as we can, so we can divide both sides by -8. And now we're going to rewrite this in exponential form because you can see that our variable is trapped inside the logarithm. So 6 to the power of -1 equals x minus 5. And then 6 to the power of -1 is simply 1/6. And this would give us 31/6. So then before I box it, let's go back and check. So again, really all we're checking for is that this value, so we want to make sure that x minus 5 is greater than 0. So when I plug in 31/6 minus 5, I get 1/6, which is greater than 0, so our answer works. All right, let's try another one. So here's a case where we don't really need to isolate the logarithms because we have a single logarithm equal to a single logarithm. And as long as the bases are the same and there's nothing else being added or subtracted, we can actually just take these expressions and set them equal to each other. Because if the logarithms are equal and the bases are equal, everything else must also be equal. So we could say 4x squared minus x equals 72 plus 3x squared. So this is just a quadratic, so we'll set our equation equal to 0, and this one we can solve by factoring. So we get two solutions, 9 and -8, but we need to go back and double check. So first we need to actually check both logarithms. We need to make sure that 4x squared minus x stays greater than 0. So we can plug in, let's start by plugging in x equals 9. So 4 times 81 minus 9 is greater than 0. So yes, that will definitely check out. And now let's plug in -8. So 4 times 64, and then it becomes plus 8 is greater than 0. Yes, that works. And then let's also check our second logarithm. Again, that must be greater than 0. So you can see that when we plug this in, it's definitely greater than 0. And when I plug in -8, this is also definitely greater than 0. So both answers are correct. All right, let's do another one together. So here you can see that we have the sum of two logarithms and then equal to 4. So for us to isolate our logarithm, we actually are going to want to condense these two into a single logarithm, which we can do using our product property. So they do have the same base, and it's the sum, so we are going to do the product of what is inside both logarithms, like this. So this becomes log base 2 of x squared plus 14x plus 40 equals 4. And now that it's isolated, we can rewrite in exponential form. So here we just have a quadratic equation. So of course we're going to set our equation equal to 0. So we get x squared plus 14x plus 24. And here we can solve by factoring. So we get two potential solutions, negative 12 and negative 2. But let's plug those both in to check. So for this first logarithm, I need to check both logarithms from my original problem. So whatever our x value is, we need to make sure that this stays greater than 0. So if I plug in negative 12, you could see that that is not greater than 0. So I don't even need to check negative 12 with the other one. I know that this is actually an extraneous solution. Let's check negative 2. So we have negative 2 plus 4 is greater than 0. Okay, that one works. And now let's check our other logarithm. We need to make sure this stays greater than 0. So negative 2 plus 10 is in fact greater than 0. So x equals negative 2 is our only solution. So just remember, whatever expression is inside your logarithm, the overall outcome must be greater than 0. All right, I have one more for us to try together. So here we have two logarithms, or the difference of two logarithms, actually natural logs. So we can condense those two using our quotient property. And now we can rewrite this as an exponential equation. Okay, from here, we do need to solve for x, so we're going to keep this as e to the power 4, just so our answer is exact. But first I'm going to multiply both sides by this denominator. So e to the 4th times 2 minus 2x equals 2. And then we can distribute, so 2e to the 4th minus 2e to the 4th x equals 2. And then I'm going to subtract away this number, 2 minus 2e to the 4th. And then I can divide both sides by negative 2 times e to the 4th. So we get 2 minus 2 times e to the 4th over negative 2e to the 4th, which if I simplify that, because this, and this are all divisible by 2, or we could say negative 2, we get negative 1 plus e to the 4th over e to the 4th. Notice I can't divide by e to the 4th because I can't just simplify part of my numerator. This is a sum that is all divided by e to the 4th. So this is as much as we can simplify, and this would be our exact answer. And I know it looks a little bit strange to leave an answer like this, but it's okay to leave an answer with e to a power, because again, it's more exact than getting a decimal approximation. But of course, before we do anything else, or I should have done this before we boxed our answer, we need to make sure that this logarithm stays greater than 0. So we're going to actually plug in our entire thing. And for this, you could actually just type this into your calculator to see what you get. And what you end up with is a positive number. It's about 0.04 if you round. So again, all we care about is that it is greater than 0, so we know that this is our solution. And again, we'll leave this as an exact answer. All right, so at this point, I'm going to ask you to pause the video and give this one a try on your own. All right, go ahead and check your work here. So you can see that I condensed these two logarithms into one using the product property, then rewrote it. And then here we just have a quadratic. So I set equal to 0, I divided both sides by 3, and then I had something that was factorable. So we get two potential answers, but we need to make sure, again, that this value in here is positive. So whether you plug in the negative or the positive version, you'll get positive 9/2 here, which actually simplifies to a positive number. So both are solutions. All right, here's our last problem of the video. So please pause again and give this one a try. All right, go ahead and check your work here. So I condensed using the quotient property, and then I rewrote as an exponential equation. Then here it's just solving for x. Make sure you simplified your answer. And then we do need to check to make sure that this 8 minus 3x remains greater than 0, which it does. So 9/4 is a solution. All right, that is all for today's video. Thank you so much for watching.